Hi, welcome to lecture 22 for multivariable calculus. Today we're going to talk about divergence and curl, and small apology as my CSS is a little off here, so the fonts and the background looks a little different. And most days I don't feel like tracking it down, so we'll just power through. So we're talking about divergence and curl. So the plan today is to first introduce them via Green's theorem. All right, it's a little different than you might see in the textbook, but we've already done all the work with Green's theorem. It naturally spits out divergence and curl from there. But then we're going to move up to 3 dimensions, where we're going to be for the rest of the semester, and we'll give some formulas for these two concepts, divergence and curl, hopefully give you some idea of what they measure. And lastly, we'll introduce some really nice notation that'll help you remember formulas there. So for this little comprehension, don't worry about formulas too much, certainly not until the end there. Worry about just overarching concepts. In lecture, we'll pound on some examples and really drive it home how to use them. All right, here. Okay, so what are they, these two notions, curl and divergence? They're measurements of change of a vector field. So in calculus, we've been measuring change all along. So here's a quick differential calculus in 30 seconds. So we started in one variable calculus. We computed instantaneous slopes. So that was a rate of change. We divided change in output divided by change in input, or rise over run, when we were really measuring slopes here. Anyway, those were scalars, and we got a scalar out of it. Then we looked at curves. Right? Again, we had a rate of change. What was changing? That was position was changing. So that was a vector. Right? You had a difference in positions, the vector, divided by a change in time. That's a scalar. Right? That gave us a vector. Right? So it was still a rate of change, but it was a change in position divided by change in time. For scalar fields, these are functions of several variables. Things got a little more weird. We realized there were lots of different change happening in different directions. But then as we looked at it, we realized we just had this one nice object, the gradient, right? So that also, in a sense, is a rate of change, although not in quite the same way. It is a vector, right? It tells you how the scalar field is changing. You can figure out how it's changing in any direction from that vector, right? So it was a really neat object. So now we're here at vector fields. How are we going to talk about how they're changing here? Scalar fields were complicated enough. Vector fields are going to be a lot more complicated here. So there actually is something called df, but that's a total derivative that we'll approach in later classes, really. But instead, we can understand how a vector field is changing. And Green's theorem is going to offer us some answers, not all the answers, but some answers about how do vector fields change, how can we measure them. And so we go to the ideas of circulation and flux. These were two things we measured with line integrals, right? The things that appear in Green's theorem. Let's talk about circulation first. What are these things? So they are from line integrals of vector fields around closed curves. It's really, I use the word circulation when we have a closed curve here. But start with this definition, which you should be familiar with. All right, what is the line integral of a vector field around a curve? It's the line integral over that curve of f dot the tangent vector, right, to the curve. So t here is a unit tangent vector to the curve. We take those dot products and we add them all up with respect to arc length. That gives us the integral of the vector field. So when it's a closed curve here, that's why I give you that thing of circulation around C. But once we have that idea, right, that we can measure circulation around a little loop, then we can get a little more clever. And for a given vector field, we can start talking about the circulation density, right? How much spinning curl is there in a vector field? So this formula down here, don't memorize this, don't even write it down here, but just look at it now and think about what it means. We're going to get a much nicer formula in a second. But this thing is a rate of change, like we've been measuring rates of change so far. It's, right, the ratio that we're comparing is a bit more complicated here. So what are we doing? We're taking our vector field. We're going to home in on a particular point here. And then d sub r right there is going to represent a little disk of radius r. Notice r is going to be going to 0. All right, we're going to look at what happens to this ratio. When r goes to 0, we're zooming in on this point in question. So we've got a ratio, right, a numerator and a denominator. On top up there is circulation. So it's circulation around a little disk, right? So we can measure how much circulation is there in our vector field. And as that disk gets smaller, we're kind of thinking, okay, right, if I look at closer and closer, right, is the vector field kind of moving around in a circle? Is it circulating at all? I'm dividing by the area, so at least it makes sense that we might get an actual number out of this. So you've got some circulation on a small scale, but you're dividing by area on a small scale too. So when we kind of zoom in on a particular point, we're just asking, is there a ratio between the amount of circulation I see around a disk divided by its area? Here's a picture, I know, crude picture of what's going on here. So I've got a vector field, and then I'm going to zoom in on a particular point over here at the center of this little circle right here. And when we get close enough, you can see that, oh, we've got the little tangent vectors floating around the outside. So what does circulation measure? We do a line integral around this little point, and we ask how much is the vector field kind of circulating around it here. But notice there's this idea of sign. Our vector field agrees on top. You kind of see it pushing along top. The vector field still is pointing to the left on the bottom, but not as strong. Right? So you can kind of see that there's going to be net positive circulation here. You can see the arrows a little better if I flex them out a little bit and back down. All right, so they're all pointing counterclockwise here, and the vector field pushes more left on the top than it does to the left on the bottom. So in the aggregate, we get some circulation around here. Sometimes people talk about, if we imagine if this vector field were lines of some flow, right, and we were to pin some object down, like pin a feather or boat or something on a little buoy at this point, what would happen to it in the flow? Would it spin, kind of counterclockwise? Would it stay still? That kind of question. So that's what curl measures. Right? It's circulation per unit area. Right? We would do this on a finer and finer scale as we went down. But Green's theorem tells us what's really going on here. Right? So Green's theorem says, oh wait, you want to measure circulation? I can tell you how to do that. Instead, measure a double integral of this thing, right, over that area. So we're going to measure instead this double integral over area. And this guy on the right, is rigged a bit. It has a very particular form. Right? What is this thing? Again, don't write it down, but just look at this guy here. I'm taking a double integral of a scalar valued function and dividing by the area. Right? If that sounds like average value, it's exactly what it is. This is the average value of this integrand here. And so if we take a limit as r goes to 0, it's one of those facts about continuous functions that if you take an average on a smaller and smaller level, right, as you squeeze down to 0, you just get back the function itself. Right there. So that means the curl of f, which we think of as the circulation density, I like that word there, tells us kind of at a point how much is it spinning. Right? Now, that doesn't make sense a priori, right? How can something be spinning at a point? Right there. But I'll remind you that slope at a point made no sense once upon a time too, right here. And so this is exactly of a kind. If we want to talk about how much is the vector field spinning at a point, we want to do this. We want to measure spin, right, and then check the ratio on a smaller and smaller scale there. Okay. If you missed all that, you should just see the left and the right end of this. What's the curl of a vector field in the plane? It's this scalar, right? We call it the scalar curl. It's the integrand from Green's theorem, dq dx minus the p dy. All right, we'll come back to that. But first, let's look at what we call flux, which is just the same picture that we had before, except now when we zoom in, we're going to look at how much the vector field is flowing out through this little loop here. So that means instead of looking at the tangent vector, we're looking at the normal vectors pointing out. And so now the question about my vector field is, okay, right, I want to know kind of how much is it changing? How much is it kind of pointing outward of a little loop, right, of a little disk around a particular point? And that is what divergence is going to measure. Think of the word diverging, right? Running away from there. We want to measure how much of the vector field running away from a particular point. And so that's where this quantity comes in. Again, vector field, right? So we're measuring some ratio. What is the ratio? But just instead of circulation, it's flux out of the disk here. So I do a little line integral around the outside of the disk. I take the vector field and I dot it with the normal vector. You can see that over here. So that gives me flow out. And so I do the same trick. I go on a smaller and smaller scale, and I say, okay, this vector field, and as I zoom in, is stuff flowing out from that point, or is it flowing in? Right? And we get the same idea as before, and Green's theorem tells us exactly what's going to happen. I again get an average value, but this time it's not the curl, the scalar curl. This is what we call the divergence. It's this measurement of the components. I take the x derivative of p and the y derivative of q, and I add them together this time. So it makes them a nice complement to curl. So again, we've got two measurements for how a vector field is changing. How much is it spinning at a point? That's the curl. How much is it diverging at a point? Is it expanding? That's the divergence here. So to sum up for the 2D case, and again, this is just the 2D case, right? We've got the curl of f, qx minus py. I call it the circulation density. If we get a positive number out of that, because it's a scalar, remember, in 2D, a positive number means counterclockwise spin. You can think of good old right-hand rule. Again, right, when you're looking at the plane, put your fingers in the direction of how your vector field is spinning. Your thumb will point up if it's counterclockwise. So you get positive, right? It'll point downward if you have clockwise spin to get negative. And if it's zero, we say the field is irrotational, right? Meaning kind of something sitting in a flow with that vector field won't spin one way or the other. And there we'll see lots of irrotational fields in time. All right, flip over to the divergence question. Again, this is for a vector field in the plane in 2 dimensions. Right? We'll call divergence flux density. It's this formula, px plus qy. Right? That one you have to know here. And a positive number means kind of expansion, right? Meaning the vector field's flowing out from a particular point, and a negative is compression. It's coming in here. So right, divergence again is a scalar. And if it's zero, we say right, there's incompressibility, or rather it's an incompressible flow. And there are lots of things that behave that way. If you just take water, for example, for the most part, it's incomprehensible, right? Squeeze a water balloon, what happens? Bulges on the other side, right? It's hard to really compress it in any way. And we can mathematically say that, saying that the way water moves, its divergence is zero. It can move all over the place, right, and be changing. It just turns out that the right, it doesn't stretch out, and it doesn't compress either. Okay, 2 good formulas to know, right? Again, we're just in the plane here. So what about 3D now? All right, so we've got a vector field with 3 components, and we'll use P, Q, and R, right, for the third one. Sort of a natural setup for a general vector field in 3 dimensions. There, divergence works out really well. It's pretty much the same thing, what you would have guessed. It's also a scalar. It measures expansion. Right here, its formula is just the x derivative of the first one plus the y derivative of the second one plus the z derivative of the third component here. Right, so you just add up those 3 partial derivatives. Right? Just go down the line, take the x derivative of p, the y derivative of q, the z derivative of r, and add them up. Right, so you get a scalar function here. Again, positive expansion, negative compression, 0 incompressibility. More maybe useful for the water analogy to be in 3 dimensions where water is flowing. Everything's great. What about curl? Not so much. Here's the formula for curl, and there's a lot to take in there. That's a formula. You have to know it, but I'm going to give you an easier way to remember it. Before you try to memorize it, let's just look. One thing that should come screaming out to you: curl in 3 dimensions is a vector. It's not a scalar anymore, right? It's got 3 different components. And they're weird. This weird combination of partial derivatives is how you form the curl. Fortunately, it's not that weird. It still does measure circulation, if you like. But when you move up to 3 dimensions, you got to think circulation is not as easy a thing to understand. In the plane, we got away with a scalar, right? And that's because in a plane, there's only 2 ways to spin, right? Clockwise and counterclockwise, right? Yeah, and that's it. In 3 dimensions, that's not the case. And I'll use my little prop here. Good old, all right, soccer ball here. So how can things spin in 3 dimensions? Well, of course, there's lots of different ways that we can spin a soccer ball, crazy. So one scalar is not going to tell me which direction it's spinning in, but the cool thing about 3 dimensions is that no matter how you move a soccer ball around, right here, it turns out, all right, as long as you keep it in the same place, no matter how you spin it, there are always exactly 2 points, right, that are fixed, right? Or I guess all the points are fixed if you don't move it there. In other words, there's always an axis of rotation right here. So every time I'm moving this guy one way or the other, there's always an axis of rotation. And so a vector can describe, right, spin in 3 dimensions. Right? You don't need more words than that. One vector does it. It's the vector of the axis of rotation here. So this is really neat. That's what the curl does for you. It says, okay, I've got a vector field in the plane. I want to know how is it kind of rotating at a point. Well, it turns out it comes from zooming in right, really close and then watching what the net result of following the vector field does to something in space. And how that's going to move, right? The answer to how that's going to move is a vector here. And the vector points in the direction of the axis of rotation. And more to that, it's a vector has direction, right? An axis is just a line. A vector has direction. It's even better, right? So the direction of the vector there tells you not only the axis of rotation, it tells you the direction of rotation, right? So this way versus this way. I've got an axis of rotation here. Right-hand rule tells you which way it's going. So if you know the curl of a vector field, put your thumb in the direction of the curl. Right? The vector field is turning in the direction of your fingers. And the bigger the magnitude of the curl, the faster a spin you get right there. So this looks like a horrible formula. I won't say it's not horrible here, but it's pretty neat that it all the information it carries. It's still a rate, right? How much spin is there in my vector field here? But it's a little more complicated than just simple ratio here, right? It's a vector that packs in all that information. The direction tells you the axis of rotation, right, with the right-hand rule, and then the magnitude tells you how fast it's going. I made this little animation here that I just meant to, not answer every question there is about curl, but at least give you some picture of what's going on. So I've got a 3-dimensional vector field here, and we zoom in on a particular point. The little dots are just supposed to be like dust to show you the flow of this. But as you zoom in at a particular point, right, over here, right, you see there's the vector pointing down this way, and the little dust particles here are the flow of the vector field. And you can kind of see they're spinning a little more on the outside, away from the z-axis here. So we'll zoom back in a second. So this flow is spinning around the z-axis, right, but it's spinning faster on the outside than on the inside there. And so the net result of that flow is we get a little spinning action at any given point, and it points down to reflect that sort of this direction that it's spinning in here. And so that blue arrow is the curl of the red arrow vector field at that point there. Right. Again, don't overinterpret it and don't drive yourself crazy looking at my terrible code to generate that. Okay, so I told you there was a way to memorize these formulas, and there is, and it's almost too neat in a way. So we use something called the del operator, this little character here. The character is called the nabla, if you want to look up the character, but the operator here is called del in some text. What is this thing? So it looks a little weird here. So it's a vector, but I put a vector in quotes because it's a vector of operators, right? Okay, d dx, that's not really thing here. It's kind of like there's a piece missing there. But we think of this as an operator. It's a thing that differentiates with respect to x. Right? So if I were to feed this thing a function, I could get a number out of it here. Same with ddy and ddz. So don't overinterpret what this thing is. Just say, okay, it's some notation I can use to memorize formulas. But it is pretty neat. So I've got the x derivative in the I, the y derivative in the j, and the z derivative in the k. Right? It has nice symmetry there. So what we're going to do to this vector is we're going to apply it as if it's a vector using vector operations. All right, so I'm going to pretend for a second it's a vector. I'm going to do vector operations I'm allowed to do and see what happens. And of course, you get something very nice. So start with scalar multiplication. Right? You can multiply vector times scalar. So interpreted here, the vector is the del operator. The scalar is a scalar valued function, little f there. So that's what I mean by scalar times vector. So you see that here in the middle, right? I've got the vector is the operator, the scalar is f. And if I multiply them, and again, I should put a lot of quotes on here, but we put them together, right? Vector, scalar gives me vector, and that's the formula for gradient, right? You knew this notation already, but now it kind of fits, right? Something, a callback from week 1 where we were doing vector times scalar is vector here, except now vector is the nabla operator, the scalar is a scalar valued function, right? And the output, right, is the gradient, right? So that thing's a vector there, right? Works out nice, nicely there, right? You already knew the gradient. Why did I introduce that? Because now let's take the same del operator and let's look at the dot product, right? So what can I dot? I can dot vectors together, right? But now in this context, the vectors I'm going to dot are that vector operator del, right? You see it here, and a vector field now, right? So when I say a vector, it's really a vector field, a function that spits out vectors. And the dot product now, remember, vector dot vector gives me scalar. But if I do my dot product, remember, I take the first component of del, which is the x derivative. I apply it to p. I do my second derivative of del, is the y derivative of q. And then I take the z derivative of r. Dot product tells me to add those up. Right? I get the divergence. So just to keep track of that pattern, right? Scalar multiple, right, gives you gradient. Dot product here gives you divergence. And so you can guess what the next one is, which is really nice, is the good old cross product, right? So here's that crazy formula we saw before. We'll now take a vector like a vector field. We'll take as our other vector the del operator here and suspend disbelief that that's really a vector, because it's not. But this is a way of just memorizing a formula, but it's quite neat indeed. So I've got a cross product here. My two vectors are the del operator. You see that in the second row, right? Partial x, partial y, partial z. F, right, is the vector field. It has 3 components, p, q, and r. And now let's take the cross product here. So remember how that works. I'm going to take I times dy dr. And so that's not multiplication there. That's kind of application. I'm going to take the y derivative of r, and I'm going to subtract the z derivative of q. Right? So when I go backwards, I get a negative sign on there. Right? And then I switch to the next guy. Right? I look at the j component. How does that work? I'm going to take the z derivative of p, or it's j, so that one gets the plus this time, minus the x derivative of r. This way. And then lastly is the k component. All right, how does that work? I take the x derivative of q, I subtract the p derivative of y. And so that gives us, right, this nice cross product. That's the curl formula we saw earlier. Right? These components, again, ry minus qz, right? pz minus rx, right? And qx minus py, which you might recognize our friend here in the z component, right? That was the old scalar curl right there. So it works out if our vector field is only in the xy, right? Only has xy components, right there, and it's independent of of z, right, then the only part of the curl that survives is the scalar curl, the one we know here. So there's a really nice symmetry to this formula, and a really anti-symmetry to this formula. If you notice, the first component involves the other two variables, right, y's and z's. So you can think of this as circulation around the x-axis, around the y-axis, and around the z-axis, if you like. So it's not too awful of a formula at all. Okay, so sum up here, right? We've got a bunch of different derivatives here. We talk about the in and the out. So what do you start with? You start with a scalar valued function, right? With one variable, you take its derivative, you get a scalar valued function, right? That's what we mean by in and out in this little chart here. Partial derivatives, same idea. Scalar valued function goes in, scalar valued function goes out, right? So you can think of this little operator that's like a scalar. Gradient, right? Scalar value f in, but vector comes out, right? Because we have, right, we're thinking of vector times scalar here, right? With our del operator. Divergence, vector field goes in, so that's what I mean. Vector in, scalar comes out, right? So the divergence gives you a scalar to measure how your vector field's changing. And lastly, by far I think the most complicated one is the curl of a vector field. Only works in 3 dimensions, but you knew that because cross products only work in 3 dimensions here. The input is a vector, the output a vector, and now you know of a formula for computing it. There. Okay, so hopefully that made some sense. We'll work a bunch of problems in our sessions, and hopefully this stuff will sink in a bit better. I will see you then.